So, I don't want to spend a lot of time on this. What I was hoping you would answer for these salaries of Americans is a distribution which is skewed to the right, almost always. 2, to compare the incomes of two different groups, what are you better off comparing? Medians? In a skewed distribution, what is it that's closer to the skewed end? The mean? 4, what is it that's resistant to outliers? That's the median. What numbers do you need to make a box plot? The 5-number summary, or you could have just named them. The low, the first quartile, the second quartile, the third quartile, and the high. 6, how do you find the interquartile range of a group of data? It's Q3 minus Q1. 7, in a box plot, the interquartile range is, I guess you could just say the length of the length or the height, I don't care how you say it, of the rectangle. Length of the rectangle. 8, in calculating the standard deviation, after subtracting the mean from each value, what's the next step? To square those differences. And 9, what does a smaller standard deviation look like in a histogram? A histogram that's more compressed horizontally. It's skinnier. A big standard deviation, wide. A small standard deviation, narrow. So anyway, does anybody, you can let me know if you have any questions about that, but that's how that went. Let's see. Who are you? Remind me. You weren't. Who else came in? Ryan. Ryan, you need yours. Anybody else come in while I was talking? Okay. So, today you're supposed to have chapter 2 ready to go. Starting off with the questions to remind, you want to go through some difficulties, we could talk about them.
I couldn't get my Excel to make to do the standard deviation. Can you just go through the steps again?
Standard deviation? The calculation.
Yeah.
Yes. Okay. I'm going to need some data. Let me see. We'll go to the website, and this is chapter 2 stuff. So let me go back to chapter 2. So the question was, could I please go through a computer standard deviation again? So I'm looking at chapter 2 to get some data. Do you have any suggestion on a problem or a data file?
I just couldn't get it to go at all. Well,
I just don't know if one of these...
2.9,
Exercise 2.9? I'll try that one.
That's the one.
Okay. That helps. So we're loading the data file here. Okay, and so to do a standard deviation, you would first click year 2007. Okay, well, then it's slightly different. Tools, data analysis. On mine, the only difference is it's data analysis, so we're almost together. From here on in, it's the same. Descriptive, that's correct. Click OK. And then you want to click and drag on the data that you want to find the standard deviation of. While the cursor was flashing in that top bar, you can see it grabbed it here. That's good. Click on an output range, and then make sure you click in this tab to the right of it. While that's there, choose a spot for your report. I always like I don't know, stick it out to the right. Make sure you check Summary Statistics, and then click OK. That should be enough.
It wouldn't do anything. It just kept telling me that I didn't have anything in my output range, even with the cursor in the
Okay, well then, if that, boy, it's hard to say. Then maybe what you could do is just, instead of choosing output range, choose, what does it say, new page? I'll do it again. I can't remember the exact words. Anyway, here's the report. And the only thing I don't like is it comes out a little scrunched, and you can't see, it looks like standard DV, and if you just drag that bar to the center, you can see the whole word, but there it is, 1.982. Now, let me just show you one more time. If we do data analysis, I want to show you another way to get the output, because it sounds like your hang-up is the output range.
Right.
Descriptive statistics, okay. Click and drag, same deal. And instead of doing output range, I think this is the way it comes up as new workbook.
Mm-hmm.
You can just leave it like that too. And now if you click OK, it'll give you the same report, but it'll just put it on a new page. And maybe that's your only hang-up. Okay, let's see if that gets over it. Other questions about technical things or items from Chapter 2 assignment? Yes, I think so. What page are you on? Could you tell me what page that's on, Natasha? 50. Thanks. And that's 21? Okay, California counties. If you're planning a sample survey of households in California, you decide to select households separately within each county, and to choose more households from the more populous counties. To aid in the planning, Table 2.3 gives the populations of California from the 2000 census. Examine the distribution of county populations both graphically and numerically using whatever tools are most suitable. Write a brief description of the main features of this distribution. Sample surveys often select households from all of the most populous counties, but from only some of the less populous. Well, so it sounds like they're asking you to plot the distribution and to look at and to analyze it. So they want you to do a graph and this kind of thing, the numerical. So what I would do is I'd begin and I'd make a histogram. So I would go back. Let's get rid of this one here. And let's get rid of this one here too. Move that out of the way. Let's go back to our website. What was it? Table 2.3? Okay, so here's our table. So first, old stuff. Do a histogram. Remember? You want to do data analysis, histogram, click OK, input range, click and drag on the populations. Actually, I'm trying to think if we can get the labels in here automatically. Oh well. They're in alphabetical order, I guess. So for right now, I'm not going to worry about that. Okay. Let's say output range, and let's put it off to the right. You can also do the new worksheet thing, like we were just talking about. Make sure you click a chart. Let her rip. Then you just got to unmidgetize it. Whoa. Happens to me sometimes. I guess I really unmidgetized it. Anyway, so you got a histogram. Looks like we have some outliers here, don't we? Now I would do the descriptive statistics. So data analysis. This time descriptive statistics. Click OK. Click and drag on the data. Okay, let's do the output range somewhere down in here. And we want summary, okay. I must have done something. Okay, let's go back and just do that again. Yeah, I must have not had my cursor highlighted, so let's do that one more time. Input range, click and drag. I know what I did. I like the way it tells you. Okay, I didn't have my cursor flashing in here before I chose my output range. So now choose, and now it should work. Okay, so we got our histogram, although I made it a little bit too tall. Let me undo that. Okay, so we got our histogram, we got our descriptive statistics right to the left of it. Now we could make some decisions on, like, how many are you going to take from each county? Okay, and or how many are you going to take from different sized counties? Now remember what this means. This means what? This is the number of counties with 0 to 1,208. And then this is the number of counties with 1,208 through this big old number. And then this is the number of counties, etc. So, I would do something like this. This comes out to about 1. This one comes out to about 50. So, since there's a 50 to 1 ratio there, I would say, well, you could say, for example, we could take 10 from this, get 10 people from one of these tiny counties. We could get 500 people from the counties that fit in this area. We could get, I don't know, what is this, about 30? We could get 300 from there. What did I just, not 300. 30. And over here, we only have about, what, 2? So there I get 20. So if I pick that, then can you see that I will get a fair sampling according to how our distribution came out? That means where I had more people, where I had more populous counties, I'm obviously going to ask more people. And where I had less representation, I'm going to ask for less surveys. So in other words, we're asking for surveys in proportion to how many there were. That's pretty fair. I don't know, something like that I think is what they were looking for. Now, this idea of me saying, if there's 1 here, let's pick 10, that was just my arbitrary decision. I could have said, let's pick 1, let's pick 50. The only thing is 1 person. I don't know. And so, or I could have said, let's multiply everything by 5. So let's ask 5 people this, let's ask 250 this, always in proportion. You got it? Does that make sense? So that's what they were looking for, is some kind of a fair distribution. So if I just ask all the size counties the same number of questionnaires, then aren't the little people, I mean, then I'm misrepresenting that big group. And so you want to kind of have it be proportional. Excuse me. Sorry. I don't know. Is that enough for you? Okay. Another question? Yes.
13.
Number 13. Let's see what's going on there. Where are the doctors? Table 1-6. Number of medical doctors per 100,000 people in each state. The distribution is right skewed with several high outliers. I'd probably want to do it a histogram just to see that. Anyway, then it says, do you expect the mean to be greater than the median, about equal to the median, or less than the median? Because it's skewed to the right, doesn't that tell us that the mean is going to be to the right? Because isn't the mean always out toward the skewed tail? So I would say greater. Why? Because, and then I just say, the mean is always, what? On the side of the median toward the skew or something like that. And then it says calculate x bar, calculate the mean and the median, and verify it. So in other words, show me, in this particular case, and you could do it using descriptive statistics, show them that the mean is really greater than the median in this case. That would wrap up A. What's B? District of Columbia is a high outlier at 758 medical doctors per 100,000. If you remove DC, because it's a city rather than a state, you expect X bar or the median to change more? Why? Okay, so in other words, if you take the outlier out, now what's going to happen? Yeah, you got the idea. And in fact, you could, if it wouldn't even hurt to actually take it out, redo it, and observe it. And then you don't even have to do any guessing, but yeah, you got the idea. Because the outlier will definitely what? Won't an outlier, if it's really extreme, cause the mean and the median to be more separated? So if we take the outlier out, just like you said, they're probably going to be closer together, aren't they? If you take that, what did I say? If you take the x, let me try my words again. So if you take the outlier out, won't the mean and the median be closer together? Yeah, like you said. Okay, I'm going to collect this assignment. So let's do that now. Now I know you've got papers scattered, so all I ask is that you put them together. I don't care if you don't have I don't have a stapler in here. I probably should have, but I always forget that. So I'll tell you what I'll do is I'll just cross pile. Just give me your pile. The next person's I'll cross pile. And when I actually look at them, I'll staple them for you. Okay? So if you could get your papers together.
I have an issue because I didn't finish the whole thing. I was sick of doing everything.
Write me a little note or something, so, because there's so many. I get about 60 of these when I call. I can't remember. So if you can get everything together, here's one. Here. Well, you don't have one handy, so what I'm doing is I'm just cross I'll keep them together. See what I mean? So that'll be Are you guys over here? And the quiz is back, so afterwards I'll get to yours. Any others? Remember, my primary goal in this is pretty much to see that you did the work and that you didn't just copy things from the back. You know, you work things through. And then I was also looking, remember, for the part computer, part manual. Okay. All right, let's get started on Chapter 3. And reminder, this is the last chapter of our first test section. So I don't know if I can project yet, but I'm going to make a rough guess. Today is Friday. We're starting Chapter 3. We'll for sure need Monday and maybe a little bit of Wednesday. That means by the time we review, probably the test will not be next week, but the week after that. Okay, so right now I'm going to project not this coming week, but the week following that, probably Monday-ish. I don't know for sure yet. Early in that second week after, okay? And this test will be a test that has no computer involved in it, and it's going to be a lot like the questions you're doing in your assignments, that type of thing. Okay. So we'll keep posted on that. I thought we'd start off with a slide that talks a little bit about where we've been and where we're going here. I'll get a little summary. Well, I think we've found this out. It's always good to plot your data one way or the other, either with a histogram or a stem plot, because a picture still gives you an important view of the data, overall relationships. You can tell outliers right away. Maybe you can't exactly spot the center, but you have a pretty good idea where to find it. You can see if it's skewed or not. And if it is skewed, right away you know something about the mean and the median. It says number 2, look for an overall pattern. Sometimes the spread is a big deal. And if you got a really short, wide distribution, that tells you stuff too. We also learned how to calculate in Chapter 2, calculate the center and the spread using all kinds of neat things. Now we're going to go to number 4, I guess you could say, in this chapter. It says sometimes the overall pattern of a large number of observations is so regular we can describe it by not just a bunch of jagged bars, but a smooth curve. And that's kind of my, I guess you could say that's my intro to where we're going here. And it's chapter 3. And this is all about the normal distributions. Now let me make a comment. First of all, the curve that I have shown on the picture here is the normal distribution curve. Now, I shouldn't say the normal because there are many normals. But every single one of the normal distributions is symmetrical. Some of them might be skinnier and taller, and some of them may be fatter and shorter, but they're all symmetrical. Perfect match between the right and the left. And this is a huge chapter for this reason. So many types of data fit the normal distribution curve. It's actually astounding. In fact, later in the course, we're going to come upon a theorem that still to this day floors me that it could possibly be true. And it's really cool because this thing affects over 90% of studies that are done. Anything that's natural, like things about people, things that the biologists will study, where they're studying different types of life. When you take statistics, and you take a lot of them, you keep coming up with this really regular shaped curve. Of course, you got to have a lot of them. If you have a dinky little sample, then who knows what you're going to get. But if you have a really healthy sample, this is what keeps emerging. So because this is so common, learning how to deal with it becomes incredibly important in this course. So the first thing we want to talk about in Chapter 3 is something called density curves. I should maybe, this is what the book had for the learning objective, but actually it could have also said, not just interpret it, but identify. What is a density curve is the first thing I want to talk to you about. And to introduce this to you, you'll notice we've got some kind of a curve. And by the way, curves don't have to be curved. When we use the word curve in mathematics, we mean graph. And so a curve literally could be a horizontal bar. It might be curved like this. It might even be like triangular shaped or hexagonal shaped. So please don't get hung up on the word curve. In mathematics, curve means kind of like graph. Okay? But here we actually do have a curve, and what we're interested in is the area under the curve, that greenish shaped colored section up there. You know, down to the x-axis, what's the area under the curve? Well, we're going to be talking a little bit about probability in this chapter. Probability relates to, you know, what are your chances? And all the chances, you know, it's kind of like, I'll just take a head, flipping a coin. There are only two possible outcomes if you have a normal coin, even though my dad taught me otherwise. I mean, you're supposed to either get a head or a tail. And if it's a fair coin, there's a 50% chance that it's a head, and there's a 50% chance that it's a tail. And when you add those two up, they add up to 100%. They have to, if it's good probability. By the way, you're probably wondering about what my dad said now, so I'll tell you. He had this thing. He'd come home Friday from work, and he would say to us, "Hey, well, I grew up in Milwaukee, and my dad had a bunch of brothers and sisters, and so we had all kinds of cousins. And so on Friday, he'd say, well, who should we go visit this weekend? And it was always, you know, one of the relatives. And I would always get a vote in for the boy cousins, so I could go over there and play, you know, that kind of thing. And my sister would always vote for the girl cousins, you know, makes sense. And my dad would say, okay, thanks for the input. But this is so confusing. He says, here's what I'm going to do. I'm going to flip a coin. And if it's heads, we're going to this grandma. If it's tails, we're going to this grandma. And if it stands on end, then I'll flip it again, and we'll see which boy, if we go to a boy or a girl cousin. You always see, you know, if it stands on end. Well, not a very realistic possibility, is it? He was just joking. He wasn't really that hard of a guy. That was his weird humor. Because we really did go to the boy and girls cousins quite a bit. But anyway, there really isn't a chance. I mean, you know, when they go out for the Super Bowl toss, they're not going to say, well, heads, this team gets to choose, and tails, this team gets to choose. And if it stands on end, then we'll go to the booth, and we'll have them decide. That doesn't stand on end, so, okay. So anyway, but the key is that all the probabilities have to add up to 100%. In a probability curve, all the area under the curve has to add up to 100% or 1 in the same way. Okay. Here's another example of a curve, and you can see, in this case, we're just interested in the area under the curve between two particular things. Just trying to get this concept. And then, like I said to you, curves don't have to be curved. Sometimes they might even be triangular shaped. Okay, here is a curve. I know it doesn't look very curved, but it is. What's the area under here? Well, length times width, right? The width, I guess you could say, is what? 10 units. The height is 1/10. And what's the length times the width? What is 10 times 1/10? 1. And that's exactly what we want to hear. Because the area under this curve is 1, this is a probability distribution, a density curve, excuse me. So let me just write that on here. So we've got length times width. In this case, it's 10 times 1/10. So therefore, this is a density curve. So what's the key thing for it to be a density curve? The area under the curve has to be 1. Let me just say area. If the area under the curve is 1, you've got a density curve. And it's okay if it's not curved, if it's just a straight bar like that. Here's another one. Let's check if this is a density curve or not. I know it's a little bit hard to read, a little bit fuzzy. This number here is 20, this number here is 40. So the width of this is 20. The height of this is 0.05. So now the question is this a density curve? Well, if you take 20 times 0.05, you get 1. So this one works too. So length, width, area is 1, so this is a density curve again. Therefore, you guys seen that symbolism before? A little triple dot like that in a triangle form is a shortcut in mathematics of saying therefore. Therefore, this is a density curve. How about this one? Well, this is a triangle. So I'm going to make you stretch back into your geometry roots a little bit. How do you find the area of a triangle? Remember? That was unintentional. It was base times height divided by 2. Now, what's true of B and H? Perpendicular. So, because I have this on a grid, you can see the height, can't you? What's the height? 1. And what's the base? 2. So it's 2 times 1 divided by 2, which is 1. So this is a density curve also. So a density curve is any mathematical graph that has an area underneath it of 1. And that's because we're tied to probability, and you know, to do probabilities, you got to have everything always add up to 100%. You know, for example, I mean, if the weather says, if the weather forecaster says the chances of precipitation today are, I don't know, 92%, then in effect, what is he telling you are the chances of not having precipitation? 8%. And when you add them together, you've got the complete picture of 100%. So if they probability, things always have to settle on 100%. Okay. Now, this part is review, so you can probably rest a little bit here. In fact, originally I didn't teach this in Chapter 2, but you remember the difference between the mean and the median when we have a symmetric distribution and a skewed one? I know you do, because I made a big deal out of it. In a symmetric one, the mean and the median are right together. When you have a skewed distribution, you know this, the mean is always what? More toward the skew. In this, the green is the mean, and you can see the green is to the left of the blue here, to the left of the median. Whereas in this one, which is skewed to the right, the mean is more to the right. And then we talked about this crazy thing too. Okay. Now, normal distributions. Okay, we're used to looking at these histograms, and when you really, really take huge files, what happens is you get, this thing starts looking so regular that you can begin thinking of it, instead of a bunch of bars that are jagged on the top, you can think of it as this nice, smooth curve in red. And that's kind of the idea. So this is the idealized form, and you'll see me showing the smooth curve quite a bit. Nothing wrong with a histogram. It's just that, you know, when you have an infinite number of bars, then it looks really smooth. Okay, now remember I promised I'd tell you what a standard deviation, I try to relate to you what one standard deviation really is. Okay, here's a normal distribution curve. That curve I was just talking about, nice and smooth. There's a point right here that has special meaning. You'll notice it's right on this division between the blue and the red section. What's going on here is, up here, you can see that the curve is what? Opening downward. It's curved downward. But obviously over here, isn't this thing curved upward? You see what I mean? This one's turning downward. Isn't this turning upward here? The question is, where does it change from turning down to turning up? And you can just about eyeball it. It's right there. And that's exactly where one standard deviation is. Okay? So, how did I say it up here? It's where the curve changes from curved down to curved up. And that's exactly one standard deviation to the right of the mean. Well, the same thing is true over here. Here, this too is the point where it changes from curved down to curved up. And this would be one standard deviation to the left. And by the way, it shouldn't surprise you, where's the mean? Right in the center, right? And because this is symmetrical, where's the median? Right on top of it. Yeah. Okay. So, the other day when we got a standard deviation of, I don't know, 7 point whatever, that means from here to here is, in that particular problem, was 7 point whatever. And now you can at least picture what a standard deviation is. And if you go 1, 2, 3 standard deviations to the right and 3 standard deviations to the left, you basically have, I don't know, 99.98% of the data. So all I need is 3 either way, and I got everything. So at least you have a feel now, a little bit more, for what a standard deviation is. It's that turning point. Okay, now we're going to transition to a few additional symbols here. On the left, this is what we've been using up until now, right? You've seen this. This stands for the mean, and we've been using, I think, S or SD, the standard deviation. Okay, that's true. That's true in a sample, like sample surveys. When I have the entire population, then we use the Greek letters. The mean is the Greek letter mu. And by the way, the Greek letter mu has the that's like their M. And so guess why they use it? Mean. M. Makes sense. Why did we use X bar? I don't know, but we did. Standard deviation, S. Standard deviation, sigma. Same S. This is their S. By the way, do you remember what the capital sigma looks like? I know you do. Remember that? Sum? It's that funny looking, what? Almost like an E. This is their lowercase sigma. I know, you're thinking it's kind of funny. Well, they probably think ours is hilarious too. Okay. So, to differentiate, when we talk about a whole population, we'll be using these symbols. When we talk about a sample, we'll be using these familiar ones. And an incredibly important formula in this chapter is called standardizing a score. And here's the formula. It's pretty simple. You take whatever the score is, x, subtract the mean, mu, and divide by the standard deviation, sigma. In effect, what that does is it tells how many standard deviations is that to the left or the right of the mean. So in other words, tell me what that score means in standard deviations. And boy, is that powerful, because you can take two things that are totally different scales and actually compare them. I'll give you an example. remember earlier I had said this about let's say you came back to your dorm room and one person said, hey, I got 8 right on a quiz today. And then the other guy says, yeah, well, I had 7 right on a test. I'm sorry, I had 9 right on a test. And he's like, ha ha ha, so I did better than you. Of course, that means nothing unless you know that the guy who has 8 right on that quiz had 8 out of 9. And the guy who had 9 right had 9 out of 200. Obviously, the guy with 9 did not do better. Well, standard deviations is going to allow us to compare totally different scales, even 1% and the other one something else. So like, for example, which is better? A certain math ACT score or a certain math SAT score? They have totally different scales. How can you tell? Use standard deviation. That's where we're headed. And it's incredibly powerful. In fact, we're going to do an example just like that. Okay, so that, I guess we've spent long enough on that. Okay, and then this probably will be our last thing for today. The same curve, you know, I've got it divided into colors. If we go 1 standard deviation either way from the mean, when it's normally distributed, there will always be 68% of the data between those two. The lead blue section of the curve is always going to have 68% of the data in it, every time. And if you go 2 standard deviations either way from the mean, you will always have 95% of the data. And if you go 3 either way, every single time you're going to have 99.7% of the data. This is such a big deal, and it will come up so many times that we even give it a name. We call it the 68, 95, 99.7 rule. We're gonna need this in order to solve problems in this section. Okay, we're out of time. So what I'd like you to do is get in reading your chapter 3. Nothing more formal than that. Start taking a couple notes. Ask yourself, you know, maybe even write a couple questions down in your notebooks. I'll see you on Monday. Have a good weekend.